begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. We thank you for the rain, which renourishes the earth. And we thank you for this class that we have. I just pray we would be, you'd be glorifying what we do here, that we would come to a good understanding of the idea of numerical integration and what remains in the last section. Lord, in your name I pray. Amen. All right, so I have one more nefarious substitution to show you. And I'm very tempted to try another problem because Dr. Skimbordas just told me that this problem being hard, so I kind of want to try it. Technically speaking, I'm supposed to do numerical integration with you today, so I better do that. But if we have time, I'm going to try that other integral. Let's see here. The square root of 1 plus e to the x dx. How do you do such a thing? So this is from a section 8.6 integral. It's another one of these rationalizing substitutions. So we want to make some substitution. It's again an implicit substitution, which removes the radical. And here's kind of a rather kind of just like in your face, I'll just call it u. Okay, so like there. Now the radical has become u. Ooh. This may have to do with that talk. So I don't know. So let's see here. So du is what? 1 over 2 times the square root of 1 plus e to the x, right? Times e to the x dx. Which is what? This is u again, right? So I've got e to the x dx over 2u. Now, in order for this to be useful, I need to get rid of that e to the x. How can I trade e to the x for some sort of algebraic expression in u? It's interesting how much of the light in this room comes from that window. You know, like when it's dark outside, there's just like one window there, but it's so much darker in here. Isn't it weird? Well, my impression is darker. I don't know. Maybe that's just me. Let's see here. So how about if we square this? What do we get? We get u squared is 1 plus e to the x, right? And then it's pretty obvious how to solve for e to the x, right? E to the x is u minus 1, and we find du is equal to what? U minus 1 dx. Oh, yes, thank you. So then going back up to here, we've got u squared minus 1 times dx divided by 2u. All right, so my thought bubble is complete. Let's go put it into practice over here. What do we got? We've got the integral of u. And what's dx? My thought bubble is not quite complete. I really should solve this for dx, right? Here. Let me open my thinking again. All right, so dx, we got 2u du over u squared minus 1. So we got what? We got ourselves 2u du over u squared minus 1 for the dx term there, right? You guys with me? Does that make sense so far? I mean, of course, there's a larger question asked here: is how on earth do you decide what to make u? And I really don't have any kind of overarching advice for you, except that I've shown you 3 examples. So at least be able to do examples like the 3 I've shown you, right? The Weierstrass substitution, the rationalizing substitutions, just for algebraic expressions, and now this one. So, I mean, with integration, there are no guarantees. Things are going to work out nicely. So this is what? This is 2u squared over u squared minus 1 du. Well, that is what? That's an improper rational function, right? So we got to come to terms with that. I'm going to use my adding 0 trick. So this is 2 times u squared minus 1 plus 2, right? See what I did there? See what I've done? I've subtracted 2 and I've added 2. The reason I did that is so that I get a copy of 2 and then plus a proper rational function. I get 2 plus 2 over u squared minus 1. Sorry, I have to write it over here. I've been told it's fun. I can't help myself. I'm saving this for later. This is apparently monstrous. Or was it cosine of 2x? Oh, man. I'll have to look at one of your books later. Okay, I digress. So this is what? This one we can, let me just do the partial fractions for this over here. To get from here to here, I'm going to use this thought bubble. So I've got 2 over u squared minus 1, but that's like a over u minus 1 plus b over, it doesn't really matter which order you put it in. I'm putting it in this order because I want it to work out and look a certain way. And, okay, so you do the usual song and dance. This one I can actually guess, but I'll behave. So a times u plus 1 plus b times u minus 1. And so I'll call this thing Pac-Man. What should we feed Pac-Man today? -1. So we get 2 is equal to minus 2b, right? So therefore b is equal to minus 1. If we feed Pac-Man 1, we get 2 is equal to 2a. So therefore a is equal to 1. So what you got over here is the integral of 2 plus 1 over u minus 1 plus 1 over u plus 1 du, which I can integrate, right? This is what? This is 2u plus the natural log of the absolute value of u minus 1 plus the natural log of the absolute value of u plus 1 plus a constant. Okay, so that's, sorry, this was just to get from yes, thank you. Correction in red. There we go. Thank you, thank you, thank you. Excellent. All right, so then what? We're not done. We got to go back to what? Yeah, exponentials and x's and such. So what you're looking at here is twice the square root of 1 plus e to the x plus the natural log of the absolute value of square root of 1 plus e to the x minus 1 minus the natural log of the absolute value of square root of 1 plus e to the x. Brandon's excited about something. I can hear him. He's yelling at them, probably about bad algebra. Let's see here if I had to guess. It's Calc 1, so on the other side of the wall. Let's see here. Plus a constant, right? Now this, I think, is actually section 8.6. I think I did this is maybe number 3 or something. I might have even assigned it in homework. I haven't looked at your, I guess I could look. I've got the list right here. Oh no! Oh man, this is one of your homework problems. What have I done? What's that? I shouldn't have told you. You wouldn't have noticed. Now that said, I mean, so here's the deal. Like if I'm on a, if it's a test, all right, and if I haven't given further instructions on the test, then what I just got to, in my humble opinion, is a decent answer, right? The integration's done. I put it back in an x. It's a reasonably simple formula. Now, this is an odd problem. If you look at the book, right? If you look at the book, the answer is not that. The answer in the back of the book is as follows. It is minus x plus 2 times the square root of 1 plus e to the x plus 2 times the natural log of the square root of 1 plus e to the x minus 1 plus a constant. And so if you look at this answer, which is from the answer key in the back of the book, and you look at this answer, you might be a little bit disconcerted. I mean, you might be like, well, am I doing this right? Yeah, yes, we are doing it right. That is, in fact, the same answer. I'll even show you a little bit of why. So, if I was to want you to get to that answer, I probably would say something like, show by integration that this integral produces that. I have to be careful to say show by integration because any reasonable student otherwise would just do what? If you're asked to show that the integral of this is that, what would you do? What should you do? No, you should not integrate. If I give you the answer, all you have to do is differentiate it. And you should see that the derivative of that is this, right? That would suffice to prove it, unless I gave you the instructions, integrate. Explicitly integrate to show that that's the formula. So if I do that, then if I said that instruction, then you'd kind of be stuck with going through these things. I mean, what's the easiest method of integration for any given integral? Complete and total knowledge of integration, right? Like if you know the answer, then you can just write it down, right? This is guessing, right? You sometimes forget guessing is a viable method of solution in math. There are people who have guessed things in very abstract contexts and made their career out of it. They don't have to say where the guess came from, right? They just have to show it works. That's also true at your level. But then again, we get into these conspiracy theories as professors. Oh, did they cheat? Not usually. Okay, so these two things can be put into this. Square root of 1 plus e to the x minus 1 divided by square root of 1 plus e to the x plus 1. I mean, if you cheat on your homework, you're just you're just making your test all that much harder. So cheating on the homework is dumb. Cheating on the test is also dumb because I might catch you and then you have a mark on your record. You don't want that. I don't want to do that either. Anyway, I'm speaking vacuous comments. It never happens in here. So square root of 1 plus x minus 1, because you guys actually care about your education and you want it to be genuine. All right, square root of 1 plus x. So that's properties of logs, right? Then here's the thing. You can take this, right, and you can multiply the inside. You kind of like do a rationalizing thing in the sense of removing the root from the denominator. If I multiply by this, right? And when I do that, what I get to is something like natural log of what? Well, downstairs, so I get a 1 plus e to the x minus twice the square root of 1 plus e to the x plus 1 upstairs. And downstairs, I get 1 plus e to the x minus 1. Let me call this thing ghost. So ghost simplifies to what? Well, you notice that the downstairs, what do you got? You got 1's cancel. And so you got like minus the natural log of e to the x, which is what? Right, so let's see here. Otherwise, we've got what? We've got 2, right? Or how can I say this? We've got 1 plus e to the x plus twice the square root of, or rather minus twice the square root of 1 plus e to the x plus 1. Let's see here. And then that, of course, you can look at that as what? This takes a little more imagination, but this we can look at as the square root of 1 plus e to the x minus 1 quantity squared, right? So you see this simplifies to the x, or rather minus x, right? There's the minus x. This 2 plus square root of e to the x was also down here. I just failed to copy it, right? That's over here. See it? That was there already. So you got this, you got that. Let me just write it over here. That was also present. I forgot to bring it over to here. So we got that, we got that. This is precisely this once you pull the 2 out, right? And then plus a constant. So that's how to get to the answer in the book. So as you're comparing your answer to like what's in the book, you have to keep in mind we know these properties of logs and we know algebraic manipulation, right? So this advice to you is not just for this course. Maybe you're working in a differential equations class later. You might want to check your answer versus what you found versus what's in the book. You always should keep in mind these kinds of manipulations of the answer. Or, of course, you could take the answer in the book and differentiate it, see if it's right. You could take the answer that we came to, underlined in red back here, and to see if it's right, all you got to do is differentiate it and see if the derivative gets you back to the integrand. If it does, you're right. So there's a simpler way of checking your answer. And it's not the case in here that part of the instructions for a given problem are find the answer in the back of the book. That's not something I put on you. All right? It's not something I do put on you. I insist my grader be smarter than that. I want my grader to be able to see if you did the integration correctly, if you come to an answer which is right, which is logical, which is based on the methods of integration which I've showed you, you should get the answer counted right. So like this should be a legit answer. The reason I'm showing you this is I want you to understand that the book is not wrong and that it can be simplified. And I guess this is a simplification of that answer. I mean, fine, it is, right? So it's a worthwhile discussion. All right. So any questions about this before I go on? All right. So I need to talk to you about numerical integration for a little while. Numerical integration, let's see here, is section 8.7 in your book. And there are 5 major methods of numerical integration that we teach at this level. And numerical integration is just what it sounds like. It's integrals actually using numerical methods, explicit formulas with numbers and such. So the basic goal of numerical integration is to find a good approximation to the definite integral, at least in our context, right? So how do you approximate this thing? We wish to approximate for various reasons. There's a lot of different reasons you might want to approximate an integral. The first and sort of most obvious reason that you might want to do this is it could be, perhaps f of x such that f prime of x is equal to f of x is difficult or even impossible to determine in closed form. We've spent the better part of our effort this semester finding closed form antiderivatives for functions in terms of other elementary functions. It's a much harder question to answer. When is a given f of x? When is it impossible to do such? But there actually are algorithms for that. I think Risch's algorithm or something like that actually gives a definitive answer to that. That's why Mathematica and other computer algebra systems like Maple, so forth, are successful in doing symbolic integration, is because there is a specific algorithm that you can go through that will basically say you can or can't do an integration in terms of these elementary techniques. But there's other things that are more insidious than this. Maybe you're working in an application, all right? And it could be that you don't even have a formula for f of x. Think about this. It might be that you don't even have an actual formula for f of x. It may be that all you have is some kind of data set which describes the function, right? That's a possibility. That's a real possibility in applications to the real world. So it could be that not even f of x is known, let's say algebraically, in terms of a formula. Could be only a data set describes y equals f of x, perhaps from some experiment or something. To calculate the derivative in such a context, you actually have to go back to the definition and think about average rates of change. And how would you best approximate the average rate of change given the data set? I once disparaged the definition of the derivative while a professor was observing my class. I said, yeah, the definition of derivative doesn't really matter. You don't really need to use it for computations. I was a young graduate student. I didn't know better. And he was very upset. He's like, my whole research is about using the definition of the derivative directly to analyze data. I'm like, oh, sorry. I was just talking about how to do problems in calculus for calculus students. Oops. Anyway, so if you look at a picture of this, and we'll think about positive f because it's easier to draw the picture, there are just a few, and let me make a more boring picture like this. I'll try to draw the same one. I'm going to regret this. Well, we'll see how it goes. So the first thing you could do to go from, say, A to B, right, you could use like boxes. And that would, for my silly example, what would this do? These are supposed to be of equal width. I fail. So the width of these boxes, of course, is what we call delta x, change in x. The height of these boxes, so, to set this up, we need to talk about a partition. Remember back, we talked about partitions when you defined integrals, so like a would be x naught and b would be xn. So you have x naught is equal to a, you have x sub j is equal to a plus j delta x. And how do you figure out the width of each box? Delta x is what? How about this total distance, right? B minus a. How many boxes do you have? By definition, n. Okay, so b minus a over n gives me the width of each box. So like x1 is, you start with a and you go delta x over, right? There's x1, here's x2, and so forth. So what I've pictured here is what's called the left endpoint rule. In fact, this would be sort of a picture of L6 for this. L6 is actually equal to the sum I equals 0 to 5 of f of xi times delta x. This is the left endpoint rule. Yes? Yeah, x sub naught, the 0th x. Yeah, no problem. So that will be the left endpoint rule. Obviously, this is an underestimate because our function's increasing, right? There's always a little bit you're missing at the top of each box, right? Each approximating rectangle falls a little bit short. What would be the next kind of thing you might try? Apparently I've drawn it with 5. What if we choose the other endpoint, like this, right? Again, going from A to B, I'm going to stop the labeling of the x0 through xn stays the same for all these, okay? This is the so-called right endpoint rule. This is R5. Because for my picture, it's R5. That would be the sum I equals 1 to 5 of f of x of I delta x. That's an overestimate for this particular function, right? If a function was decreasing on the integration region, in that case, the story switches over, right? Then the left endpoint rule is an overestimation. The right endpoint rule is a underestimation if the function was decreasing. Okay, guys, what would be the next level of sophistication you could go with? Right. Yeah, we could use the average of each subinterval. So I'm drawing the average points in dotted lines here. I personally, I don't know what the book calls them. I haven't memorized the notation in the book or anything. So this would be x1 bar, and x1 bar would be x1 plus x2 divided by 2. It's the midpoint, right? So like in general, x bar j would be equal to xj plus xj plus 1 divided by 2, the midpoint. And so this gives us the so-called midpoint rule. We judge the height of each box by the midpoint. Now, is the midpoint an overestimate or an underestimate? Well, that kind of depends on whether what your function is. That's more complicated. I don't know right offhand. You know? I really have to stop and think about that for a while to give you a good answer on when is the midpoint rule an over or an underestimate. You know, that's something we can think about, ponder a little bit more deeply. But in any event, what I've illustrated here, what's the formula for that? It's M4. What we're looking at is the sum I equals 1 to 4 of f of x sub I bar delta x. So all three of these first rules basically just involve different choices of sample points, right? Either left, right, or midpoint. And we're just adding the areas of rectangles together. And intuitively, you see what happens, right, guys? As n goes to infinity, we get a better and better and better approximation, right, to the actual thing, which is the area. Now, of course, Salas and Hilly, they discuss this carefully in terms of upper and lower sums to come up with a somewhat rigorous definition of what the integral even is. All right, so the next level then, beyond these two, these ones I'm actually going to have to look up the formula for because I can't just tell you the last two. The last two are trapezoid rule and Simpsons rule. Trapezoid rule you could do for any number of approximating regions because I'll just try to illustrate it for 4, n equals to 4. So basically what's going on is, let's see here, basically it's a game of connect the dots, you know? So like, it's going to be hard to see in my picture. And you add the area of these trapezoids up, and that gives you an approximation to the integration. This would be what's called, I think, T4. Now, the explicit formula for that is given. This is called the trapezoid rule. It's number 4 on page 435. I don't have room to write the good formula for it. I'm going to write the formula over here for it, if you don't mind. Geometrically, it's just what I said. You calculate the area of each trapezoid, and you know, add those areas up, and that gives you what the trapezoid rule says. Now there is a super sneaky shortcut formula for it, which is nice. And so the rule is, and you can derive this, Tn In fact, there's also a super sneaky rule for mn, which is on page 435. But the super sneaky rule here is b minus a over n. That's basically delta x, right? And then the formula simplifies to, I'll write the actual simplest one. Do f of a plus 2 times f of x1 plus plus 2 times f of xn minus 1 plus f of xn. Now I can describe to you why this formula is true pretty briefly. How do you calculate the area, say, of like this one? What's the area of a trapezoid? It's almost right, but it's actually, it's f of x1 plus f of x2, which would be the two different heights, let's say, divided by 2 times the base. See, that gives you the average height. And if you think about it, you can take the triangle that's above the average line and you could cut it out and glue it back below it, and you just have one rectangle, which is the height of the average at the endpoints, and that would be how to get the area of the trapezoid. If you forgot that, well, it's okay, unless you've been teaching children how to find areas of trapezoids recently, in which case, shame on you. All right. Anyway, that's the area. So you see what happens if you add these up, right? In the middle, there's always 2 of each, f of xi for every midpoint, right? So you get 2 copies of like x1, 2 copies of x2, 2 copies of f of x3 when you add these up. But then the endpoints are in isolation, and that's why we have this formula over here where we have this one more precisely could be what? F of b. So you get the endpoints in isolation, and you get twice of each middle point, interior point to the partition. This is the trapezoid rule. Now, the last one is much more adventurous. This is known as Simpsons rule. Simpsons rule has to be done for a even number of, I will only be so foolish as to try to illustrate it for 2. So here's your x1, b is x2. And so what Simpsons rule does is says, well, trapezoids, come on, we can do better than that. Why don't we approximate the area with parabolas? So Simpsons rule says you fit the parabola from here to here that fits these points basically, and then up to the limits of my artistry, you can't see the difference between. You fit parabolas. I mean, it won't be exactly on the function, but man, it's going to be close, right? So Simpsons rule is based on fitting the data parabolically. Now, Simpsons rule, again, has to be done for an even number of data points, but here's the formula. And I suppose, we could easily spend an hour deriving this rule. I think I can derive the trapezoid rule in about 10 minutes. I already showed you half of that story. Simpsons rule would take me longer. But here's the formula that will come from that derivation, which I will not do for you in here. I'm going to save my energy for other things later. So b minus a over 6n is f of a plus f of b, all right, plus 2 times f of x1 plus all the way to f of xn minus 1 plus 4 times the averages. In my notation, x bar 1, f of x bar 2, f of x bar 10. Close parentheses. And again, it is not at all obvious why this, right, gives you the area of these parabolas. All right. So there's your. Those are your basic methods of numerical integration: left, right, midpoint, trapezoid, Simpsons rule. So of course, these. In terms of what I would ask on the test, I would ask conceptual things like which is a better approximation, right? For a given kind of function, left, right, midpoint, based on, say, geometric data, increasing, decreasing, concavity. There are also error estimates. So there are specific accounts for how far off one of these is for a specific n from the actual area. There are specific error estimates. I'm going to talk about that probably another day, because I don't think I have enough time to talk about it today. I'm still looking for the right. There has to be a website, all right, guys, where these things are illustrated with specific functions that you can look at and kind of see how they work. I have a link left over from last time I taught this course 5 years ago, and when I go back and look at that link, you can do it. Come on, man. Oh, HDMI, yes. All right. When I look at the link, I get this, which is fascinating, but I don't know where to click. And I haven't figured that out yet, so sorry. But what I can do for you guys is show you how to do some of these things in Wolfram Alpha. Now, I don't know, we could Google. I will spare you watching me Google these things. I'll try to do that on my own time and bring a report back to you, but I am quite certain that there is a website out there that will illustrate the trapezoid rule and Simpsons rule, all right? I can figure out, I'm pretty sure I can show you how to do like the left or endpoint rule for a given function. So let's actually try to put this into play. Let's do an example. So let's try to integrate something like, I don't know, how about the cube root of 1 plus e to the x from, say, 3 to 7. Right, so what do you guys want to do? What kind of, let's like I said, let's do left or endpoint. Let's try left endpoint rule. Let's try to approximate. Is approximately given by, what do you guys want? Let's start with like L. This is a starting point. Let's try to do L4, right? So what do we have? We have x, x of naught equals to 3, and then what's, sorry. All right, so if that's the case, what's x sub j equals to? It's equal to 3 plus j times delta x. What's delta x equal to? 7 minus 3, which is 4, right? Divided by, forget about the n here. Let's try to do, forget about the 4 here. Let's try to do it for n, just to set up. So 4 over n. That's the delta. That would be x sub j. So what is f of x sub j equals to? The cube root of 1 plus e to the xj, right? Which is unpleasant, but here it is. It's the cube root of 1 plus the exponential of 3 plus 4 over n. So to actually do one of these things, I have to figure out what is the formula for the nth, for the jth, partition point. I feed that formula to the integrand's formula, which in this case is the cube root of 1 plus the exponential. I actually kind of believe we could do this integral using a rationalizing substitution like we did at the start of today, but I also believe that I don't want to. And then what? So ln would be what? Ln would be the sum. We do sum what? J equals from what? J equals 0 to, oh, I'm sorry. Goodness gracious, guys, there's a very important thing I left out here. This is constant. This is no J dependence. What am I missing? 2 errors here. 2 errors. You guys are allowed to make corrections, Like, I don't have absolute authority in here. You can like speak up and tell me you did that wrong. It is allowed, encouraged even. You guys have like a habit of not correcting me. It's not good. It's very, very foreboding for me in view of next Tuesday. If you can't correct my work, can you correct your own? No. Now, I wouldn't know this except I teach the same thing twice, so I find out about all my errors in the second section. And I have a tendency to make the same error twice. It's a character flaw, I guess. Let's see here. So there's a J here that, there should be a J dependence. It should depend on which endpoint you're on. So the left endpoint rule of order n says I'd look at the f of, this cube root of 1 plus the exponential of 3 plus 4 times j divided by n, right? And then times what? That's just the height, right? You still have to multiply by the delta x. So, by the way, since it's constant throughout, we could just factor it out, right? Delta x is what? Four over n, right? You notice that? You can factor out the delta x here if you want to, because it's constant through the whole sum. You could do that. All right. Let's try it out here. Let's try the sum from j equals 0 to 4 of 1 plus the exponential of 3 plus 4 times j divided by n. What was n? Oh, 4. So that's just 3 plus j, right? 3 plus j. All right. Close my cube root. Third power, right? And then, this is 1. So okay. All right, and the wonderful thing about Wolfram alpha is it tends to tell you something like this, right? J equals 0 to 4, cube root of that. So you have a check that what you entered is actually legit, right? And so apparently, 29.59. Was it 29 point what? Okay. Oh, so I probably should, okay. Well, let's see. What would this look like if we said, say, n equals to 10? How would this change? What do I have to do here? I'm going to be bored. I'm going to be lazier. I'm going to do 4 times j divided by 10. And that's all times what? Yeah, 4 divided by 10. All right, hopefully we don't, and j equals 0 too? 10, not 10. Oopsie, what should I have done last time? Oh man, that's wrong. What does this go from? 0 to what for 4? I mean, generally speaking, it goes to n minus 1. Be careful about that. So this, what I have there is not right. I should have had, 3. I'm going to do this one and then go back to that one for a second here. So from 0 to 9, what do I get? 21.37. Just to keep 4 decimals. Let me fix the n equals 4 one right quick. So I should go j equals 0 to 3. 4 divided by 4. I'm just leaving it like that so it's easier to change it, right? 4. So I get 19.28. What happens if we look at n equals to 100? We do somewhat. J equals 0 to 99. 4 divided by 100, right? 4j, put 100 back there, right? $22.69. Now, what happens if we just say, integrate, 1 plus, what was it, e to the x, the cube root of that, right? From x equals, 3 to x equals 7. 22.84. So we're getting closer to the answer as we go on. Now, this is important, right? Because these methods actually are what's behind the scenes here and how it actually does this kind of calculation. It actually probably uses some sort of amped up version of Simpsons rule. If you study these things more deeply, eventually you'll find out that this actually gives the most efficient solution to the numerical integration problem. If you were to try to use cubic approximations or higher order approximations, you might imagine doing that. It doesn't get you anything. It turns out Simpsons rule is like the optimal mix of sophistication of fit and ease of computation. So anyway. Oh man, we didn't get to Dr. Skimbourdis' fun integral today. Well, anyway, I'll see you guys tomorrow. Thanks.